Okay, time for some more conversation about carbohydrates. Who wouldn't want to talk about sugars after all, right? And so we need to continue with describing the handedness of carbohydrates. They're called D and L families, and gradually then how these things are drawn. So if you've seen my recordings for chapter 18 about proteins, you might recall this diagram, this picture of a famous movie star, and talk about how there are right-handed and left-handed versions of molecules, probably not in the case of people, but his name suggested a pretty good play on this whole concept. So in carbohydrates, what is it about them that makes them chiral, and how does that have an effect on how many and types of isomers they have? Well, the simplest carbohydrate that fits the definition of a polyhydroxyaldehyde or ketone turns out to be glyceraldehyde. Glyceraldehyde, yes, it's an aldehyde like it suggests. In order to be polyhydroxy, there's got to be more than one. And so you end up with 3 carbons, and the 2 carbons that are not aldehyde each have an OH group on them. The 2 compounds shown here, the diagram shown here, are for the D and L forms of glyceraldehyde. D suggests right-handed, which doesn't mean anything obvious to you, but L at least looks like left-handed, and who cares? How can you tell from the diagram? Well, there's something circled on the structural diagrams, left and right. The D-glyceraldehyde has an OH group on the right and the middle carbon, and the L-glyceraldehyde has the OH group on the left. Notice that these 2 molecules are mirror images of each other's. The arrangement of all of the chiral carbons are exactly this opposite for the 2 forms, and we call them enantiomers. I'm going to come back to that word again. Mirror image forms of the same compound, we call that enantiomers of glyceraldehyde. So the simplest one is here, and why is that chiral? What do we remember about chirality? We've got to come back to that definition and make sure we've got it clear in our thoughts. So a chiral carbon has 4 different groups attached to it, bonded to it. And if you've got 1 chiral carbon, you get the whole molecule described as chiral. And when there is a chiral carbon, there are stereoisomers. These is our new category of isomers. We had ordinary constitutional isomers to begin with. We had geometric isomers when we did cis and trans. Now we have stereoisomer because stereo suggests spatial arrangement. It's like you think about stereo sound systems. And so same arrangement of sequence of atoms, but different in 3D arrangements. They're not identical exactly because they have at least 1 chiral carbon. So if you think in terms of an aldo tetros maybe, it's going to have an aldehyde and CHOH on a couple of carbons, but we don't know which direction the chirality puts them, and CH2OH at the end. And so there's a number of ways you can have those compounds that are different in 3-dimensional space with that exact same description. So when you have a pair of mirror image molecules, we call them enantiomers, and they are not superimposable. One cannot be laid on top of the other and have all the parts line up, just like you cannot put your 2 hands together. If your thumbs line up, the palm of one hand is up and the backside of the other hand is up. So they're not superimposable, though they're exactly mirror images of one another. These molecules, in terms of biomolecules, are often distinguishable by your senses, by taste receptors or smell receptors. And so they're going to interact with macromolecules, biomolecules, differently because of their 3-dimensional chiral shapes. And so other than that, they have identical chemical and physical properties in a general sense because their functional groups and numbers of carbons, et cetera, are exactly all the same. But it's going to be things like enzymes and other biological molecules that perceive or respond to these stereoisomers, enantiomers, mirror image forms differently. The other interesting aspect about stereoisomers and enantiomers is how, and anything that's chiral is going to be a stereo molecule or a chiral molecule, is how it interacts with plain polarized light. If you've heard my recording from chapter 18, I talked about that there a little bit, how the enantiomeric pairs the mirror image forms will rotate the plane of polarized light, and that's why they're called optical isomers. And when they rotate that light, it rotates equally but in opposite directions. In other words, one would be clockwise and the other would be counterclockwise, as represented in the diagram here. The details of how you understand polarized light and rotation of it are a little bit above our expectations here, but it's curious to think about it because light coming from any particular source is going to be a wave that propagates away from the source, but it has a wave feature that's up and down, but various directions around, all directions around the direction of propagation. But if you send it through a polarizer, all the light is going one way. That's what polarized or Polaroid sunglasses do. They help to block out light of a certain orientation. It reduces glare in your vision. And when you run polarized light through a sample containing organic molecules in solution, the light that comes out is rotated now to a different direction, and you use an analyzer to evaluate and determine what angle of rotation is going to be observed based on the sample of organic molecules that are inside that solution. Weird and not exactly easily explained as a physics question, not something for us to answer. Chirality takes some getting used to, so we have to talk about it and keep making sure we get the ideas put together. All structures will have mirror images, but not every structure has a superimposable or unique mirror image. So like if you had two ordinary pencils, one is the mirror image of the other, but they're exactly the same. If you put one on top of the other, there's nothing different. Chiral compounds, chiral substances, are those that have handedness. They're going to have non-superimposable mirror images that are, in fact, unique from one another in how they are arranged because of the fact that carbon has 4 different groups attached to it, making it a chiral molecule. And the mirror image form of this compound here shown with 4 different groups represented by 4 different colors. So everything has a mirror image, but not all are superimposable on each other. The chiral ones are non-superimposable mirror images. Now, sometimes molecules are going to have more than one chiral carbon, especially in carbohydrates. And in order to figure out what's going on with these chiral carbons, you're going to look at these structures and figure out all the possible orientations for each of the chiral carbons. There are 2 compounds that have names of erythros and threose here. They are each described as aldo, think about it, how many carbons? Aldotetroses. And if you described the 2 molecules, they would be described as having an aldehyde, 2 more carbons with a hydrogen and OH on them, and then the last carbon has CH2OH. But each of the structures shown here have unique positions around their chiral carbons. Which carbons are chiral then? So we have to remember that it's 4 different groups attached to 1 carbon. And so which carbons are going to be chiral? All right, start from the top. Let's pick erythros over here at the left and the leftmost diagram. Yes or no on this carbon? Does it have 4 different groups attached? Well, it's only got 3 things attached. No, not chiral. What about the next next carbon? Woo, see if I can say the words. Does it have 4 different groups attached? Well, the top group is an aldehyde group. The left group is a hydrogen. The right group is OH. And the other group is a really big thing. And surely those are all unique. Yes, that carbon is chiral. We'll mark them with an asterisk. So that's one of them. One of them is carbon number 2 on that molecule. Then let's evaluate carbon number 3. What 4 groups are attached to that one? All right, so carbon number 3 has a hydrogen, an OH group, a CH2OH, the one I'm doing in blue now, and then it also has 2 carbons with a bunch of things, various things, and they're completely certainly different from what you see of those other 3 groups. So again, that one is also chiral. The same thing applies for all these other forms shown here. So carbons 2 and 3 in each of those examples has 4 unique groups attached to them. Remember, it's groups, and that makes them have 2 chiral carbons. And again, I'm going to try to mark these with an asterisk, kind of point out which ones are chiral. keeps your attention. Notice it always has to have 4 different groups. I can't say that enough times. You have to practice it to get used to it, probably. Now, aldotetroses, erythrose and threose, have 2 different forms each, and there are 2 mirror image pairs. And notice that all the OH groups are on one side for one form of erythrose for the chiral carbons, and the opposite side for the other form of erythrose. For threose, the OH groups are on opposite sides, if you look at it that way. But which one's on the left or the right is opposite in the 2 different forms. So there's 2 mirror image pairs. A mirror image pair is called a pair of enantiomers. And we don't like these words. It takes time to get used to them. But notice that neither form of erythrose is a mirror image of threose or vice versa. So threose and erythrose are certainly distinct compounds when you realize that the chirality, the arrangement around those chiral carbons, does in fact matter. So there are 4 unique forms of these aldotetroses. 2 of them are described as erythrose, 2 of them are described as threose. So when you have that many possible stereoisomers that are not mirror images to each other, we call them by another name. They're called diastereomers. This word is kind of a crazy word, and you're going to get used to them with time by practicing them. And these are the stereoisomers that are not mirror images to one another. Whenever you have more than one chiral carbon, you're going to have the diastereomers will be possible. More than one chiral carbon. So in these compounds, there were 2 chiral carbons, the 2 middle carbons. And the 2 erythrose forms have names. They're D and L erythrose. The 2 forms of threose are also D and L. And so each of those D and L forms are described as enantiomers. The D and L erythrose are enantiomers of one another. The D and L threose are enantiomers of one another. But there are also diastereomers. So either form of erythrose compared to either form of threose is described as diastereomers because they are not mirror images, but they're still all the same stereoisomers. In this case, they're all aldotetroses. There is one description that fits all of these molecules, but not all of the forms are mirror images to one another. And so the ones which are not are going to be the ones that are known as diastereomers. I can't emphasize enough times that these definitions are going to take some practice. Please take note of this slide and think about the terminology. We'll be using it as we go forward. It gets better the more times you work with it. All right, now, how do you know then, and how will we count or figure out how many possible stereoisomers a compound might have? And it's going to be based on the number of chiral carbons. Thankfully, that's not too tricky because all you have to do is count. And so the number of chiral carbons is 2 in this molecule, right? So for erythrose, the number of chiral carbons being 2, the number of stereoisomers is going to be described by 2 to the n, which is 2 to the squared, which is 4. So there are the 4 stereoisomers for erythrose shown here. Other compounds you can find will have different numbers of chiral carbons and therefore different numbers of possible stereoisomers. Carbohydrates have a bunch. Beware, here they come. Woo! Glucose is a carbohydrate. And you have to look at this diagram for a minute. It's kind of a funky diagram. I apologize for the poor image quality here, but it came from an old textbook that we used for some examples a while back. And I liked the diagram and kept it. The straight line down the middle where you see intersections of crossed lines, that means it's a chiral carbon. So all of the chiral carbons are represented by an intersection of crossed lines. And so there are 4 chiral carbons on those molecules, 3 chiral carbons on the middle row, and 2 chiral carbons over there again, erythrose and threose. And glyceraldehyde is the last one, only has 1 chiral carbon. So glucose has a lot of different cousins, if you will. They're all stereoisomers of it. These are all the D stereoisomers of glucose. And notice that the top group here is your aldehyde. These are all aldo, hexoses, pentoses, tetroses, trioses. And the carbons, the arrangement of the OH groups in between distinguishes one isomer from the next. They're all stereoisomers of glucose. But how many are shown here? There's only 8 here. There's not all of them here. We didn't put them all on this diagram. So there's a lot of possible stereoisomers when you have multiple chiral carbons. All right, so let's talk about enantiomers and get practice with the terminology. Which is the enantiomer of the molecule at the top? And what do we call the rest of them? So the enantiomer is going to be the mirror image. That means all of the chiral carbons are going to be the opposite orientation. All chiral carbons in opposite orientation. Only the chiral ones matter. The rest of them don't. So the chiral carbons here are right, 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 and left. So you need to find one that has the exact opposite of that. And so the mirror image of the structure at the top would then, in fact, be structure number 4. The rest of these are still all related. All of these compounds, all 5 of them, are aldoses, right? And they all have 1, 2, 3, 4, 5, 6 carbons. If you look at them, they have an aldehyde at the top, CH2OH on the bottom, and 4 chiral carbons in between. So they're all aldohexoses. Oops, yep. And so only these 2 are enantiomers. But the rest, what term applies to the other ones? If they're not enantiomers, they are diastereomers. So compound at the top with 1 or 2 or 3 are diastereomers. Wow, these take some practice. Okay, I'm going to end this recording here to keep it in shorter segments. The next recording will tell you more about how we understand how to draw these chiral molecules in a specific fashion to represent their chirality.